All right, let us look at this problem called count lucky permutations. So what's given in this problem is we are given, let's have a read. So we're given an array of integers having n elements and a non-weighted undirected graph having n nodes and m edges. Details of each edge in the graph is given to you in the form of a list of lists. Your task is to find the number of lucky permutations of the given array, and an array permutation is said to be lucky if for every node in the array there exists an edge between this and this. So essentially what a lucky permutation is, is there has to be an edge between all all adjacent nodes in that permutation. So let's look at this example. So here n equals to 3 and m equals to 2. So n is the number of nodes and n is also the length of the array, right? And so we can see that in this array, we have this 1, 2, and 3. So this is our array. We have to figure out all different permutations of the array which are lucky. So 3 nodes, so 3 factorial, 6 different permutations could be there. And which of them would be lucky? So for the lucky would be ones where the permutations where there's, so this is a graph 1, 3 and 1, 2. So let's represent all of this information on a whiteboard. So we are given this array 1, 2, 3. So there are these 3 nodes in the array, and we are given 2 edges. So we are given that 1 and 2 are connected, and we are also given that 1 and 3 are connected. Let's quickly write all the different permutations of this 1, 2, 3. So you could have 1, 2, 3. You could have 1, 3, 2. You could have 2, 1, 3, 2, 3, 1. You can have 3, 1, 2, and 3, 2, 1. And among all of these permutations, if you look at the first permutation, 1, 2, 3, the lucky permutations are the ones where there is edge between all adjacent nodes. So here, 1 and 2 has an edge, 2 and 3 does not have an edge. So this is not lucky. In 1, 3 and 2, 1 and 3 have an edge, 3 and 2 do not have an edge. Another unlucky one. 1 and 2 have an edge, 1 and 3 have an edge. So this is a good one. 2 and 3 do not have an edge. 1 and 3, 1 and 2 has an edge. 3, 2, 1. Does 3 and 2 have an edge? No. So no. So there are only 2 lucky permutations that are there. So that's the general idea. Now, how can we solve this problem? So one of the simple ways to think about, or a brute force way to solve this problem would be generate all permutations. And I would recommend you to go through a problem which just says, given an array, generate all its permutations. And you can do backtracking to do that. And when you do the backtracking to do that, there are just total n factorial different combinations, n factorial different permutations. So to generate each and every one of them, you'll have to go through each and every letter in the each and every node in the array. So the overall time complexity of generating all permutations is n times n factorial, and n factorial generally gets considered as like n to the power n, right? So that is a typical time complexity. So now if you try generate all permutations and check whether each and every permutation is lucky or not, you can do that, but you would get a time limit exceeded error. And if you look at the problem, it also sort of says the expected time complexity. The expected time complexity is n square times 2 raised to the power n. And n factorial, like I said, is sort of n to the power n, which is much higher than 2 to the power n. So we have to try and improve we have to try and improve the time complexity here. So how can we do that? Now that's the challenging part of this question. Uh, you would have to sort of have some experience with working with the dynamic programming with bit masking to be able to understand this problem better, which is the concept that gets used. So we're going to use dynamic programming along with bit masking. If you haven't ever tried this, like Hamiltonian path or traveling salesman problem and those sort of problems which use this concept, I would recommend you have a read through this. I will also try to explain it in context of this problem itself. So if we talk about this problem, essentially let's talk about uh, counting number of permutations, right? How can you count number of permutations? So counting You know it's n factorial, but like, how would you count in a general sense? So you're given, let's take example of an array where your array is 1, 2, 3, and 4, and you want to be able to count the different permutations. Okay. So number of different permutations. So you'll say, hey, I want to find all the permutations of 1, 2, 3, and 4. Well, the way to do that is you fix one element, right? So to be able to do this, you will have to first fix one at the first position and then take 2, 3, and 4. So it would be you fix one and then you get different permutations that you get from 2, 3, and 4. Add to that plus, right? You would have to do you maybe take two at the first position, and then remaining one, three, and four is your set. Now it's not in any particular order, but you sort of find different permutations of one, three, and four, and similarly you do for other three, right? So you will now fix, let's say, three as the first guy, so you will be left with one, two, and four, and similarly you can have four as the first guy, and then you'll have to permute on one, two, and three. That's the basic idea, right? Now, if we keep going down this path, let's say if you do this further, so this would be what? This would be, now you, let's say you fix two, so you will be left with three and four, right? And if you fix three, you would be left with the two and four. And if you fix four, you would be left with two and three. And same thing if you do for this guy, you can see it will be number of permutations. You fix one, you'll be left with three and four. You fix three, you will be left with 1 and 4. You fix 4, you will be left with 1 and 3. Let's just do one more for this as well. So if you fix 1, you'll be left with 2 and 4. If you fix 2, you'll be left with 1 and 4. If you fix 4, you'll be left with 1 and 2. The reason I have been doing all of this is to basically show you that there is some overlapping subproblem at some point in time. You see this P34 here, you see this P34 here, right? You see this P24 here, you see this P24 here, right? All of these different. You see this P14 here and P14 here. And if it was a bigger array, right, you would see even bigger. So the idea is uh, there is overlapping subproblems. So we have to use DP. That is one bit we sort of clarify. Now I'm going to sort of try and represent it in the DP form. So what it really means is, so let me represent. So how do I represent? So number of permutations of the string 1, 2, 3, 4 is what I wanted to find, right? Let's call this, I don't know, set. Okay, it's a set. Now number of permutations of this equals to number of permutations where you fix one, and so essentially you said I am sort of fixing one and I'm left with two, three, and four, right? Or rather, let me define it in a slightly different way. Let's say we say this as, this is equals to, there are four different cases. One is like this, and I'll say what I mean by each of them. So now what I mean by this is number of total permutations is, well, number of permutations when your first guy is one and the total number of elements in total number of so is, I'm calling this as paths. Okay, so number of different paths, so number of different permutations in which start with one and have these nodes. Number of different permutations which start with two and have these nodes. number of permutations which start with 3 and have these nodes, right? That makes perfect sense. Now, if you divide it further, what this would be? Well, this would be now you subtract 1 from this path, right? So this would be essentially the number of permutations for 2, 3, and 4, right? Basically, you removed 1 from this, and similarly here, you would have removed 2 from it. So this would be number of permutations for 1, 3, and 4, right? So this is removed set, and what would this be? Again, this would be summation of number of permutations of you take a node y and you remove that node y. Um, Basically, again, so yeah, it could be y and this 2, 3, 4 set, and where y is in 2, 3, 4, right? I know it's not very clear, but in general, we know what we're trying to do, right? So if I try to write it more systematic, so this is what I'm trying to come at, which is the number of different permutations or number of different paths in which this is the ending node or rather starting node, right? So number of different permutations which start with this node. Okay, let me clarify. So the number of different permutations that start with a specific node and contains this set, right? So this is set of nodes and this is starting node. So obviously the starting node has to be in the set, right? So this set is all the nodes in permutation, right? So this is a set that you're trying to permute, and in this set, whatever this is the starting node, then this would be equals to summation of all the different permutations where now in this set you would have subtracted this starting node, right? Which if it's x, then minus x, right? Because x is done, and the remaining guys again now it can start from any different y where y is in s minus x, which is essentially what we are doing, right? We say fix the starting guy. So you fix the starting guy, and once you fix the starting guy, and the starting guy can be all the different options, and the starting node can be all the different options in S, right? So you try each and every different option in S, take that as a starting guy, and when you add that as a starting guy, remain that guy from S. That's why you get S minus X, and then try all the other combinations recursively like that. So that's the general approach. And if you use this, and if you use the DP concept, the overall time complexity would be improved. So let's try and write the code for it, maybe in a top-down fashion, and hopefully when we write the code, it will be slightly more clear. All right. So when we come to the code, first of all, let's uh, the maximum number of nodes can only be 15, right? So we can have an adjacency list-based representation, but we can, because n is 15, we can also have an adjacency matrix-based representation because n is not that high. So let's just have an adjacency matrix-based representation. So I'm going to have a Boolean array, which indicates whether or not two nodes are connected. So we have Boolean new, let's do from n plus 1 to n plus 1. Because I think the number of nodes, I don't know whether they keep from 1 or 0, right? So we'll just, for safety, we'll do it like that. And now we're going to go through each and every edge in the graph. So each edge in the graph, let's get the two nodes. So u is edge of 0 and v is edge of 1. So we're going to do this connected of uv will be true and connected of vu will be true as well, right? Now, let me quickly go back to the whiteboard to talk about the bit mask stuff. Like, why do we need a bit mask? So here, if you see, we are saying the starting node. This starting node can be between what and what. So this starting node in general can be between 1 to n, right? So these are n. What is this set of nodes? So if there are n nodes, how many different sets can be there? There can be 2 to the power n different sets, right? So for example, for 1, 2, 3, what are the different sets? Well, there can be 8 different sets. Just 1, just 2, just 3, 1 and 2, 1 and 3, 2 and 3, 1, 2 and 3, and then nothing, right? There can be these many different sets. So for all of these different combinations. Now, how do you represent a set? You can have a Boolean array. Uh, a simple way to represent a set can also be a bit mask. What would that mean? That would essentially means that whichever index is present, whichever index you want to consider, then just set that bit, right? That's your set is. So your array has indexes from 0 to n minus 1. So your bit mask bit mask and n we have seen is less than 15. So that means your bit mask can have n bits, and whichever index is present, that bit is set, right? So let's talk about a few basic stuff. So all nodes present. How would you represent that in the bit mask? So all nodes present, or rather first, let's say um, number of masks, right? How many total masks you can create? Well, there are, it's just 2 to the power n, right? And this can also be represented as 1 left shifted by n, right? And all nodes present, what would be the mask to represent all nodes present? Well, it would be 1 left shifted by n, basically 2 raised to the power n minus 1, right? All different ones will be represented by that. Now, let's talk about this bit. Is a bit set in mask, right? So is bit B set in mask? How do you check that? Well, the way to check that would be, so whatever your mask is, you AND it with this 1 left shifted by B, right? That means the mask is being, and you are ANDing it with just a single one in, and that one is in the position where this bit is. And if this does not give you 0, that means that bit is set, right? And other is toggle a bit. So for toggling, you can use this XOR operator, right? Because if you look at this XOR, if you're same, it gives you 0. If you're same, it gives you 0. But basically, if you XOR with 1, so 1 XOR with something will be X complement, right? So that's why what you can do is here you set that specific bit that you want to toggle and you XOR it. So you do mask and you XOR it with 1 left shifted by B. So this is how we can represent uh, a set, right? And if we talk about the space complexity sort of, so now this is 2 raised to the power n, and this is n, so the overall space complexity will come up to be n times 2 raised to the power n. This is how we will represent the sets, right? So let's come back to the code and try to build that logic. So this should be clear. We're just building this. We have just built the graph here, nothing fancy. Now let's do. Let's say we want to do this. We want to return. So how? What will the lucky permutations like what we discussed? So lucky permutations would be we fix the first guy to be any index, right? So int I equals to 0, I is less than n, I plus plus, and we want to do so. it's long, so long, let's say result equals to 0. So we're going to do result plus equals to, so what do we want? So okay, let's also define mask with all nodes. What would this look like? Like we discussed, this would be this minus 1, right? All nodes are set, and we want to be able to visit all nodes. So now result plus equals to, you can say, let's say we define a helper function, lucky permutations, which will pass. So I is what we choose as the its starting guy, and we want a path which contains all nodes, so mask with all nodes, and we can pass this other information around what is the array, what is the connected thing, and anything else, maybe just this much, right? And eventually we just return result. And we say that this counting of permutations had a DP involved, so let's also create that. So how many total sets are there? We also discussed is this, right? Different sets that we can have. So we'll create this DP array of size n and total sets, right? This is all good, and we'll initialize maybe let's say to -1. So for each row in DP arrays.fill, we fill the row with -1. That's fine. So we're hoping that this DP might be useful, and because we saw there is overlapping stuff happening, so we'll pass this DP array like that. Yeah, okay, just DP. And now let's come to that helper function. So okay, all of this should go within this. Now let's try and build the helper function. So we're saying we're going to return lucky permutations, and we are saying this is the, if you're fixing a starting node as this guy, and we also have a bitmap with the nodes, bitmap with the node. Yeah, this is fine. So this is these are all the nodes that we are permuting, and within those, this specific one is the first guy, and then we pass in this other array. So we get this array, we get this connected, we also get, let's make the DP as long because the result is long, so we make everything as long. All right, so now what are we going to do in this thing? Well, the first thing, obviously, if DP is not -1, so if DP of this starting node and this bitmap with nodes, if this is not equals to -1, well, then we'll return this guy. That's the base condition. And what else? What is the actual terminating condition? So, well, one of the actual terminating conditions is this, which is you are the starting node and the map contains only yourself, right? That means the number of nodes, or the set of nodes that you are trying to permute is just yourself, and you are a starting node, right? In that case, the number of ways is one, which is like how many ways are there to, how many different permutations are there uh, when the set is one and the permutation value is also one. So just one, right? So what I mean by that is if this starting, sorry, not starting node, if the bitmap with nodes equals to this is just the starting node set, starting node, well, then your result is just 1, right? And if that's not the case, then we're going to else. And now what we're going to try? So now we remove this, so we fix the starting node, right? So when we fix the starting node, we'll do remaining nodes, right? So let's do bitmap with remaining nodes. Will be what? You remove the starting node from it. How do you remove the starting node from it? You go the bitmap with nodes, and you're gonna do an XOR with the one left shifted these many times, right? So that bit will get toggled, which is it essentially will get removed. So this is the bitmap with the remaining nodes. I know what we're gonna do. So now in this bitmap with the remaining nodes, we're gonna recursively trying permutations within those nodes. But and this is where now the thing will come in, which is the condition that is given to us that you have to be connected. And now, what are all the nodes that we're going to try? So let's try all the nodes. So for int I equals to 0, I is less than n, I plus plus. Well, one of the things is we are only interested in the nodes which are in this bit. We are trying to permute now this bitmap with remaining nodes, right? So the node has to be within this, right? So node in map, which is, and then you can check how can you check whether the node is in this map or not. Essentially what we're going to, this loop has to be really for all the nodes which are sat in this, right? And so I'm just, because n is not that high, I'm just going through each n and then checking whether it's in this or not. So if node in map, it would be, so this guy and one less than I. So this is how you would and once you you will check this should not be 0. If it is not equals to 0, that means it is sat. So this means that this node is in the map, and another thing I want to check is connected, right? Uh, it has to, and that's the condition that is given in the question, that the adjacent nodes have to be connected. So now we can do connected, and all of when all this I and all everything, this node that we're saying, it's actually the index in this array, but not the actual value in the array. But when you're looking at connected, you want to check the actual value. So we'll do array of starting node and array of I, right? So they are connected. And if both conditions are satisfied, then this is an interesting one to do. So node in map and then connected to previous. Then this is a valid path to pursue further. So let's define maybe this long result as 0. And now we're gonna do, this is the case. Basically, we're trying to put also result plus equals to, and we're gonna call this lucky permutations. And what? So now starting node would be this guy. Now we're fixing this guy as a starting node, and the bitmap with node would be this bitmap with these remaining nodes. And what else is there? So array and okay, okay, I can't reduce further. So array connected and DP is what we have to pass in. So we go array connected and DP is all the information that we pass. Let me see if I can make it full screen. Yeah, I can. So this is the lucky permutation result, and at the end of all of this, I'm gonna do save this information in DP right before returning, so that we can reuse it, and we're gonna return the result. So let's see if it and makes any sense or not. So we built the tree, which was completely fine. Then we are trying to build the, basically we are trying to count all the valid permutations, and the count valid permutations would be, okay, so I'm trying to count all permutations, which contains all the nodes and start with the specific guy. So I'm trying to fix this first guy from all 0 to n, and I'm trying to see what are all the different valid permutations which start with this guy and contain sort of all the interesting nodes, right? And then we use this DP and this bitmap with nodes. And this is the base condition where you are basically trying to permute a single element. And so that's this condition. And then what we see is, okay, so we fixed this guy, so we removed this guy from the bitmap, which was fine. And then we try to permute further down recursively. So now we're trying to see all the nodes in this. We're trying to choose them as the starting guy and permuting further, right? Which is this condition. And we only consider those nodes which are actually connected to the guy that we previously selected. So all of that is fine. Now let's try compile and fix all the different compilation errors. Okay, there are a bunch of compilation errors. One of them I can see is should be long. What else is there? Error not a statement, line number 73. Yeah, so you have to return this. All right, let's see what are some other errors. Okay, holding on, waiting. Taking time to evaluate. Maybe let's run the compilation again. Okay, line number 96. We missed a semicolon. Let's compile again. And somewhere we defined long but made the array as int. Let's fix that. I is less than n cannot find symbol. So let's define n. So n is really what? The length of array, right? So that should be fine. And the first example works. Let's submit and see if everything works or not. And it gets accepted. So now let's talk about the time complexity and the space complexity here. So clearly for the space complexity bit, you're using this DP array, which n and total sets is 2 raised to the power n. So your space complexity would actually be n times 2 raised to the power n. Let's talk about a time complexity. So if you look at the time complexity, well, for each and every of this n times 2 raised to the power n things, we are doing a further uh, for loop within this, right? So we go into this will be called for each and every this starting node bitmap with nodes combination, which is n times 2 raised to the power n. And within that, we are calling this for loop, which is running n times. So that's why the total time complexity is actually whatever is mentioned here, which is n square times 2 raised to the power n. All right, now I leave it here. Another thing to try would be to convert this top-down solution into a bottom-up, and please write those in, please figure it out on your own, try that thing, maybe add in your comment section and everything. All right,